So I guess everything's up and running now. We've got all the screens the way they should be. Okay, in theory. So here goes with the, we finished the updating. Now let's have a look and see if our intuitions are sensible. First of all, gamma 0 is a new parameter we haven't seen before, so we don't really know what to expect, except that it should be approximately Gaussian, and it is, with a mean of about minus 0.06 and a standard error of about 0.06. That's just the intercept. It's really sort of a placeholder for the uncertainty that we really have. I'll go ahead and minimize the model window so that we can focus on the things that we care about. Gamma 1, though, does have a direct scientific meaning. Let's have a look at it. So its posterior distribution looks like that, and its stats look like this. Suppose that the experimental intervention had no effect. Then what should gamma 1 be in the population? 0. Does the data, look at the posterior and look at the posterior mean and standard deviation, does the data support the theory that gamma 1 is 0 in the population? Does it support it strongly or tend to refute it fairly strongly? The signal, which is minus 0.2061, is more than twice as big as the noise. The 95% interval for it runs from a minus 0.385 right here to minus 0.028, entirely negative. So the evidence is running in favor of the idea that gamma 1 is non-zero, and that corresponds exactly to the previous story, which said that under the Poisson model, the two lambdas from the Poisson separate distributions differ by an amount that's large in statistical terms. The difference is not zero, not supported. 0 is not supported in the sampling distribution for the difference or the posterior distribution for it. Now, lambda.c should have exactly the same information as before, and if we went back and looked at it, we would see it does. And lambda.e, similarly, exactly the same information. Remember, the control rate was 0.944, and you're getting 0.944 in this model. And lambda.e has, again, a normal posterior distribution, and its mean is 0.768, which again matches the sample mean very closely. But again, with standard errors that are smaller than the ones you get from the Gaussian because of the Poisson special advantage with the variance to mean ratio being 1. And now finally, the multiplicative effect, which is a new quantity for us, has a density that looks like this. And remember, the multiplicative effect is the ratio of the two lambdas. And so if there were nothing going on, the multiplicative effect would be what? Would be 1. And so comparing the multiplicative effect with a kind of null value of 1 is like comparing the slope with a null value of 0. In fact, they're identical in their comparison. If we were to calculate 1 minus 0.8171 and divide that by 0.07425, that would be exactly the same signal-to-noise ratio as the one we got when we looked at the slope, which I guess is back here. Now, that's the gamma 0, but anyway, you get the idea. So they are one and the same in terms of their information content. And so everything seems to be internally consistent. We're getting numbers that are quite a lot like what we got from what we had before, except now what we would say on the basis of the multiplicative effect being 0.82 roughly is that it appears to us multiplicatively as though the in-home geriatric assessment intervention lowers the mean hospitalization rate per 2 years by about 18%. And the way I get that is I go 1 minus 0.8171 and multiply by 100 to convert it into percents. So it appears to lower the hospitalization rate, the average hospitalization rate, by about 18%, give or take about 7%. And therefore, the interval for the multiplicative effect runs from 0.68 up to 0.97 and does not include 1. And therefore, according to the Poisson model, not only do we have a statistically significant additive effect, we have a statistically significant multiplicative effect. So that's what we learned from that. and going back to the story here, I fit the model. We've talked about the model. I show you some WinBug screenshots so that you can replicate it yourself. And now I compare the additive and multiplicative fits. And I find that the conclusions are virtually identical, even though the additive number is not directly comparable with the multiplicative number. Because both of them are so close to 0, they are approximately comparable, even though they're on different scales. But none of this has given us a model that actually represents the data very well, because the Poisson pretends the variance and the mean are the same, and we can see in the data that that's manifestly not true. So now let's think about scientifically how we would go about improving this multiplicative model in a way that would really capture the reality of what's going on here. So the model so far says yi given lambda I are independently Poisson lambda I. And then it says log lambda I is equal to gamma 0 plus gamma 1 xi. And then we have a prior on gamma 0 and gamma 1 that is diffuse. And so I need to get the mic. And can you guys still hear me? Somehow miraculously, one battery for the whole day seems to be working just fine. I think these things don't use the battery so quickly as the lavalier mic does. I guess that's what we're learning. All right. What about how old these people are? If we knew it, the age of each person, where would we put it in the model? Would it go in the first line of the model, or the second line of the model, or would we have to make up a new line? If we knew what the person's age was, we just put it in as another covariate, right? It'd become another predictor. So let me call this one xi1 and remind you that this is the one that's 1 if experimental and 0 if control. If I knew the person's age, I would go gamma 2 xi2, and this would be the person's age. If I knew how sick the person was, I could create a score of overall sickness. I would have gamma 3 xi3, and this would be a sickness score. And the work that I do at with the Kaiser people, we're very good at building scores like that. In fact, plus down to plus, you can think of other variables that might be relevant as also. Also, I'm going to go out all the way out to lambda gamma k xik. So if we had those variables, we would enrich the model by including them. We hope that the randomization has tended to promote comparability across those variables. But you know how randomization works. It does not guarantee perfect comparability every time it's done. It tends to promote comparability when the sample sizes involved are large, and 572 is a fairly nicely large number of people. But as soon as you start adding and discover that in addition to the treatment control difference, there might be 7 or 8 other things that people could differ on, it actually starts getting hard for the randomization to do perfect matching across all 8 of those dimensions with 572 people. So, if Mr. Hendrickson, Dr. Hendrickson, had measured these things and included them in his data set that he was published, we could actually put them in as covariates, and all these gammas would be called fixed effects. And so at the moment, these things here are called fixed effects because they represent unknown parameter values that we're just trying to learn from the data. But because Dr. Hendrickson, actually I contacted him and he was not quite willing to say whether he never measured these variables or whether he was unwilling to share them with other people. But we are in the position right now as Bayesians of not knowing this stuff. What is the Bayesian approach to modeling things that you don't know? You put a distribution on them, right? And what we don't know is this entire stuff right here. And so from a Bayesian point of view, what are we going to do? The entire thing taken as a blob of stuff we don't know, the only thing we know about it is it's particular to person number I. And so why not call it, instead of having plus this, let's call it plus E sub I. In the same way with a regression model, an ordinary regression model, the error term in the model often proxies for the other covariates that were not present that you wish were in there. So I'm going to lump all that stuff together and think of these things because we don't know them. We're going to model our uncertainty about them with a distribution by thinking of each of them as like a draw from a distribution. Do we have to make the E sub i's dependent upon each other from one person to another, or is it more sensible to make them independent of each other? They're going to be independent. In fact, they're going to be IID. If we give them any mean other than 0, whatever that mean is will be completely confounded with gamma 0 in the model. So there's no value at all in giving them a mean other than 0. And let's give them a variance called sigma squared E. Look what we just did. We used science to try to describe why there is heterogeneity within each of the groups. And from a Bayesian point of view, the only thing we can do about these unmeasured covariates is to blob them together into something that's indexed by I and give it a name like E sub I. In the language of what we've been talking about all day, are these things fixed effects or random effects? They're random effects. Another name for them is they're latent variables. That's simply, the word latent simply means unobserved. When we include them in the modeling in the form of random effects, will that tend to at least describe the extra Poisson variability? Will it make things such that the variance is going to be bigger than the mean? The answer is yes, because every one of them is a normal draw with mean 0 and some variance which we think is probably bigger than 0. What if sigma squared E were identically equal to 0? Then what would happen? The random effects would be, we'd be back to the fixed effects model. Do you see that? And so this model is cool because it's a generalization of the fixed effects model. If sigma squared E were 0, we get the fixed effects model. If this is 0, get FE model, fixed effects, FE, the model that has only the two fixed effects we have so far. Very cool. So we have once again done something that's a basic standard thing to do in the Bayesian modeling world. When you have a model that is inadequate, try to expand the model. What we just did is something called, people call model expansion. And what we just did is we expanded the model by embedding the fixed effects model inside it as a special case of it, namely when sigma squared E is identically 0. How will we be able to discriminate between the fixed effects model and the random effects model? Look at the posterior distribution on sigma squared E. If it has substantial mass near 0, then perhaps the fixed effects model is fine. But we already know that it won't, because if it had substantial mass near 0, then what would the variance to mean ratios be in each of the treatment and control groups? They'd be close to 1, and they're not. Now you might say that a possibly valuable generalization of this model would be to allow the variance, the error variance, to be different in the control group and the treatment group. Because after all, the VTMR in the control group was about 1.6, and in the experimental group was about 1.3. So we could try a generalization of this model in which we let sigma squared E be one value when x was equal to x1 was equal to 1, and a different value when x1 was equal to 2. I have tried that, and it turns out not to appreciably improve the model. So I'm just going to fit this model for now.
So why didn't we, one way to go, but why didn't we say Poisson is not the right one and go back to our list of
distributions?
Yeah.
In fact, this is going to turn out to be related to what you just said, because if you look at this model now that we've added on a plus E sub I, what assumption are we making about the log lambda i's as random quantities? What distribution do they now have? Because the errors are normal, and the gamma 0 plus gamma 1 xi1 is just a constant, so what distribution do the log lambdas have? Normal. And therefore, what distribution do the lambdas have? Log normal. And so what we've just done, this is what people call a mixture representation for what's going on. It's a hierarchical is one word for what's going on. Hierarch, H-I-E-R. I spell that right? Get to the point where I can't even spell. Hierarch, H-I-E-R. Is that right? No, there's another A-R, right? Hierarchical. There we go. Hierarchical or mixture representation. And in fact, what the model says to do is that the way you would generate a Y is in two steps. First, you would generate the lambda, and then you would generate the Y from the lambda. See how that works hierarchically? But look, how do you generate the lambda? You make a draw from a log normal distribution, and then having got the lambda for that, you stick it in and make a Poisson draw to get the Y. So what we have here actually is a log normal mixture of Poisson distributions. That's what this model is about. So log normal mixture of Poissons. A lot of new ideas to think about all on one page. But this is the basis of contemporary Bayesian modeling. This is it right here. Doing your best to, have we succeeded by this device in explaining the heterogeneity within the treatment and control groups, that the VTMR came out bigger than one? Have we explained it? Well, no. The explanation would have come if we had these other covariates. That would explain why everybody has a different lambda in the treatment group and everybody has a different lambda in the control group. But have we at least described the heterogeneity in the lambdas inside the treatment group? Yes. And inside the control group? Yes. So the best thing we can do when we don't have the covariates is we can use this random effects representation to describe the extra Poisson variability. Now, to get back to your question, this is a log normal mixture of Poissons. What's another distribution that's one of our favorite distributions on the positive part of the real line, other than log normal? Pardon? Well, we're getting to that, but what's another distribution? Negative binomial is a count distribution. What's another distribution that's one of our favorites for modeling quantities that live continuously on the positive part of the real line? Gamma. And what is a gamma mixture of Poissons? It's the negative binomial. So you're right. A different way to model this data would be to say all the numbers in the control group are IID from a negative binomial distribution, and all the numbers in the treatment group are IID from a different negative binomial distribution, and focus in on that. And in fact, maybe I'll do that for next time. I'll write up the WinBugs model for that, or I could set it for homework for you guys. Now that you've got the data file and so on, fit a model that's a negative binomial in each of the two separate groups, and translate, here's the hard part, translate the parameters of the negative binomial into the parameters that we care about, namely mean in the control group minus mean in the treatment group over mean in the control group, or the other way around. In other words, the parameterization you get from the negative binomial doesn't map directly onto the mean, so you'll have to fiddle with that a little bit to get it to be what you want. But sure, so you're exactly right. A different way to go would have been to use negative binomials because they represent gamma mixtures of Poissons. Okay, so to catch up with this story here, so having done all this fancy modeling up to this point, none of what we've done so far with the Poisson models has verified that the Poisson model is any good. Oh, sorry. All that the histograms have shown is that the Gaussian model is clearly unreasonable, but the diagnostic plots in WinBugs just check the adequacy of the MCMC sampling, not the model. So in fact, we had a good clue that the data are not Poisson because of the variance to mean ratios. So there they are on this page here, which seems to be page 67 of part 4. The variance to mean ratio in the control group is 1.63, and in the treatment group 1.32. So those are VTMRs that are substantially bigger than 1, and the jargon is the data exhibit extra Poisson variability. And this actually makes good sense as follows, and now I'm going to repeat the argument that led us to those random effects. The Poisson model assumes that everybody in the control group has the same underlying rate lambda c of hospitalization, and similarly, everybody in the experimental group has the same rate lambda e, and it just wonders if lambda c and lambda e are different from each other. In reality, it's far more reasonable to think that each person has his or her own underlying rate of hospitalization that depends on things like baseline health status and age and other things. Now, Dr. Hendrickson forgot to measure or at least to report on these other variables. He may have hoped that the randomization would balance them between control and experimental groups. The only predictor we have is little x, the experimental status indicator or dummy variable. So the best we can do is to lump all of these other unobserved predictor variables together into a kind of error term E. And this amounts to expanding the second Poisson model, the multiplicative model we had before. Check it out in equation 43 at the bottom of page 68. The first line is identical to what we had before. If you knew what the lambda I was, the person's YI, the actual person's number of hospitalizations, YI would be independent draws from Poisson where everybody has their own lambda. Then the second line is identical to what we had before, except there's a plus E sub I. And now the third line of the model says, and the E sub i's are IID normal with mean 0 and variance sigma squared E. And finally we have now 3 parameters in this model, gamma 0, gamma 1, and sigma squared E. And we put diffuse priors on all of them, and we now have a functional Bayesian model that describes what's going on.
Better than you listed them in
No, you could write the hierarchy in the other order, and it would have the same logical content. Why did I pick the normal distribution here? Does it flow automatically from the science of the problem, or does it sound conventional to you, or some other reason? Well, mean of 0, but there's a lot of distributions that we could force to have a mean of 0. Is it forced by the science of the problem? Well, in a sense, there's a reason why whatever it is, it might not be unreasonable for it to be normal, because look back at this story here. The EIs are supposed to be the sum of a bunch of variables. And when you add stuff together that's noisy, you have a central limiting tendency toward the normal distribution. So ironically, if we were in the scientific situation where there were many unmeasured covariates, we would get a Gaussian just by the nature of adding those things together. Now, in fact, there's probably in this particular case study, there's probably 5 or 6 variables that really matter. And so I'm not going to argue for an overwhelming central limiting tendency based on only in adding 5 or 6 things together. But there will be a tendency for things to move toward normality by having more than one variable in this term that corresponds to the unknown stuff. The reality, though, is that people tend to put normal distributions here just because it's conventional. I mean, why do people use the normal curve as the error distribution in regression models? Because everybody else did it before them, right? Because Carl Gauss did it first of all, right? And so since Gauss did it and he was infinitely smart, we should all do it too, right? That's sort of where that normality assumption came from. It's really because back in 1805, nobody could compute with any other distribution. And so no wonder he used the normal. He wanted to compute. But this is not driven by the science, formally driven in a strong way by the science of the problem. I wish I could generalize it. And in fact, Bayesian non-parametrics does generalize it. I will show you later on how to fit this model in the following way. The first row is identical to what we have here. The second row is identical. But the third row says the EIs are IID from some distribution, and I don't know what it is. And then you go from there. And that has to be more scientifically satisfying than just slapping a normal curve down and hoping for the best. That's how Bayesian non-parametrics helps you. And I'll show you how to do that later on with Dirichlet process mixture models. So we'll come back to this data set and do it again. So quite cool. This sort of model would have been hard to fit in the 1980s and still less pleasant to fit than you would have liked in the early 1990s. But by now, we've got to the point where we're very comfortable with fitting models like this. And in fact, we are comfortable enough with Bayesian non-parametrics that we can go ahead and relax this assumption here. Instead of putting all my eggs in the Gaussian basket, I can put a diffuse prior on the set of all possible CDFs, cumulative distribution functions here, and let the data tell me what's going on. And that, in fact, is what Bayesian non-parametrics does. The result would be called a semi-parametric model because, look, we use the Poisson up here. That's a distinctly parametric thing, and we chose the linear nature of bringing in the x, although since it's a dummy variable, that's the only way you could bring it in. But this is a semi-parametric model if we put a non-parametric prior right here. And that's fine. We would want to use a semi-parametric model because we have some parametric structure. There's a very good reason for this Poisson to be here because of the story about Poissons representing the right distribution for counts of relatively rare events. The world really does work that way. You can write down a simple set of real-world assumptions that lead directly to the Poisson when what you're doing is sampling counts of relatively rare events. You just get Poisson. But the part that's been unrealistic all along is to pretend that everybody had the same lambda, and now we have a way of allowing everybody to have their own. So a little more about that, and then we'll do the fitting. The Gaussian choice for the error distribution is conventional, not dictated by the science of the problem. Although if there were a lot of unobserved predictors hidden inside the EI, their weighted sum would be close to normal by the central limit theorem. Also, model 16, the one we just looked at, is an expansion of the earlier model 11, because you can obtain model 11 from model 16 just by setting the random effects variance parameter to 0. Whereas with model 16, we're doing the more intelligent thing. We're allowing it to be whatever it is and learning about it from the data instead of forcing it to be 0. The inclusion of the random effects in the model is one way, but not the only way, to address the extra Poisson variability. As I mentioned before, this model would have two different names. It would be called a log-normal mixture of Poisson distributions, and another name for it would be to call it an REPR model, a random effects Poisson regression model. See how it has a regression structure on line 2, and it has a Poisson structure on line 1, and it has a random effects structure on line 3. Put that all together and you get a random effects Poisson regression model, REPR model, because it's as if each person's lambda is drawn from a log normal distribution, and then his or her number of hospitalizations, y, is drawn from a Poisson with that person's lambda. And this mixing process, if we did the double expectation theorem on it, we would find that this mixing process will always make the variance of y bigger than its mean, unless the sigma squared e parameter was identically 0, in which case the variance and the mean would be back to being equal again, and we'd be back to the fixed effects Poisson story. All right, so let's fit it. I'll just go ahead and kill everything here. Start a new WinBugs. And go back to the course webpage and grab the third and final model. Actually, I seem to have a model 4. That's interesting. Let's go see what that is after a while, too. Now, this model is going to take quite a bit longer to fit, although I should have parallelized it. I could have gone ahead and used our newfound parallel knowledge to make it run faster. But that'll give us lots of time to talk about questions you might have about what's going on here. So I'm going to go ahead, actually, I think I'm going to go ahead and start fitting it, and then I'll start addressing your questions. So there's our model file. Because we didn't change the data structure, because it still has that regression structure, I used the same data structure for data structure 2 that I used before when I had a fixed effects Poisson story. So I bring that in and have that be the data, like before. And now I have to have a new initial values file because I have different parameters now than before. I have a new parameter to work with, so I have an inits 3. So I have to start the gamma 0 somewhere and the gamma 1 somewhere, and I have a new tau or sigma for the e's that to bring in. Here I've just chosen to use rather specific values for tau.e and the other guys. In effect, what I've done is I've started the gamma 0 and gamma 1 numbers off at their fixed effects counterparts. And then I have an argument in the actual PDF for part 4 of the course that shows why tau should be around 2. That should be down here somewhere. What I show you around page 70 or so in the, there's the model. And on page 71, I show you what happens in earlier versions of WinBugs. If you started things off with bad starting values and you had a random effects model, it could sometimes fail to run. And it would do so with, it would fall over basically by giving you the dreaded screen that basically is a WinBugs expert programmers. In other words, the guy who wrote WinBugs, it's a debug screen for the guy who wrote WinBugs. It's not a debug screen for you or me. It's a debug screen for that guy. But if you start looking, we start seeing numbers like something or other times 10 to the minus 306, and you know that something really awful has clearly happened, and it's traceable directly to having had bad starting values. So Why are you doing this? I don't want to have you be there. So I, in fact, made a little calculation. And this warning, I think, does no longer apply in full force, but it is possible to make wind bugs fall over as far as sampling goes if you give it initial values that are enormously far from their actual posterior modes, because then it's kind of scrabbling around with a likelihood surface that may not have a lot of information and trying to get close to the mode of the likelihood, and it may not be able to do so. So it's good guidance basically to make some calculations to see what the ballpark values for these parameters should be. And so I have a little double expectation calculation that shows that sigma squared E should be around 1/2, making tau sub B around 2. In the work I did with my student Bill Brown on developing the Bayesian capabilities in the MLWin package, we didn't have this problem because there was another part of the package that already gave me the maximum likelihood estimates, which act like the mode of the posterior with diffuse priors, and so we were able to use very good starting values in MLWin. All right, but now let's go ahead and run this guy and see what we get. So once more into the specification tool breach, and the model's fine because I've used it before and made it work, and the data's fine and everything compiles okay. And now I load the inits and it complains as usual that we have uninitialized variables. If you thought the MCMC data set was ugly before, look at the structure of this model now. Let's take a moment and look at the structure. So we have one for loop for the whole sampling distribution, which defines the likelihood function. And it's exactly the same as the one before, except it has this new term plus E sub I. And now I have to add a new line inside the for loop that says what E sub I is. It just draws from a normal distribution with mean 0 and precision parameter tau.e. And all I have to do now is simply put a new prior line on tau.e, and I'm going to start out anyway by using the gamma epsilon epsilon prior, and we'll find out a bit later if that's a bad choice. Here I'm not too worried because remember I have 572 observations, and so it should be able to, the likelihood story should tell us quite a bit about what sigma.e and tau.e are, so this particular prior might not be that bad. And then the only thing I do is I add another line at the bottom that tells it what sigma.e is as 1 over the square root of tau.e so that I can monitor that as well. But look at the MCMC data set. It has one column for gamma 0, one for gamma 1, one for tau e, one for sigma e, one for mult.effect, one for lambda e, one for lambda c. And then what are the things does WinBugs have to monitor? Everybody has their own lambda, so it has 572 columns of lambdas to keep track of, and everybody also has their own EI. And so it has 572 EIs to keep track of. And so basically, it's got a lot of columns in the MCMC data set. And the result is that it's going to take a lot longer to run than the model we showed earlier. But that's just a matter of minutes rather than seconds. So let's go ahead and do it. I haven't initialized the random effects, so I'll hit gen inits to finish that off. And now let's have a go and see what we actually get. I'll do my knee-jerk update of 1,000, and you can watch how slowly it goes. It's not that bad, actually. That's good. 2 seconds for 1,000, so that won't be that bad. Okay, good. Now, let's monitor everything in sight so we can really see what's going on. So the main thing about this stuff is that if you forget to monitor something, then you have to run everything all over again, right? Whereas if you mention too many things to monitor, then you can just ignore them if you want. So get them all in there. What's that? No. It's got to actually sample all those columns anyway, and so you just mention to it the ones you want to look at. It doesn't actually make things go slower. But I will keep track of the lambdas this time. That'll be pretty interesting. And now let's do all the stuff we're interested in, lambda.c and lambda.e and mult.effect and sigma.e. Now let's get our usual 100,000 with refresh every 1,000. Let's see how that's going to go. And it's not great. 1,001, 1,002, 1,003, 1,000. Okay, it's about 3 seconds for every 1,000. So we have a while to wait. Does anybody have any comments or questions on what's happening here? Well, I'll get you in a second.
Point where model it as a log normal.
But a log normal for what? The data are count data. So we have to have some kind of count distribution for the data values. So there might be something log normal happening, but it's not on the data scale. It's on some other derived variable scale. So that's why we end up with a log normal distribution for the lambdas, because of this story about writing down fixed effects and then enriching them with Gaussian random effects. In the back? Well, that's a very good question. This model looks like it has how many parameters? You got your gamma 0, and you got your gamma 1, and you got your tau dot e. It looks like it has three parameters in it. But when we talk later on about one of the model comparison tools that people use these days called DIC, which stands for the Deviance Information Criterion, and which is built automatically into WinBugs and RJAGs, the people who built DIC, they built it especially as a tool that would generalize a frequentist model comparison criterion called AIC, which some of you may have heard of before. It was invented by a Japanese guy called Akaike, and this is how clever he was in the sense of trying to get his name to go down in history. He wanted everyone to call it the Akaike information criterion, but of course if you say that that's what you want people to do, then they won't do it because it makes you look like an arrogant asshole. So what he did instead was in his paper he named it coyly, he named it an information criterion. And the word "and" just happens to start with the letter A. And so after a while, instead of people calling it an information criterion, they started calling it Akaike's information criterion, and he got what he wanted. If he'd called it something else like JIC or something like that, he wouldn't have ever got it called Akaike's information criterion, but he called it an information criterion very coyly. Anyway, AIC, it turns out it only works for fixed effects models. It doesn't work for random effects models. So one of the main motivating factors for the WinBugs people, David Spiegelhalter and others, to create DIC was that it was a generalization of AIC that allowed you to actually, in a sensible way, cope with models that had random effects in it. And what's going on here is that the effective number of parameters in this model, if we'd let everybody have their own lambda, we would have had how many parameters, what'd we say? 572. If we make everybody in the control group have the same lambda, and everybody in the treatment group have the same lambda that might be different from that one, then we're down to 2 parameters. This model here looks like it might have 3 parameters, but in between those two extremes, it turns out that random effects act like fixed effects models with a number of parameters that is intermediate between 2 at one end and 572 at the other end. And the DIC technique was designed, it doesn't always work right, but it was designed to try to estimate the effective number of parameters. It's like asking, how much information is there in the random effects? How redundant are they in relation to the other random effects? And I think in this model, it turns out that with this data set, the effective number of independent things that are being estimated amongst the random effects is on the order of about 15 or 20. And where that number comes from, as in terms of a formula you could write down, is not such an easy thing to see. But basically, we're fitting a model that has about 25 parameters in it now by writing a model down that has only 3 fixed effects parameters, but hundreds of random effects being estimated. So it's done. It took 255 seconds, which is what, about 4 minutes or so to get 100,000 iterations. That wasn't that bad. And now we can minimize these guys here and start looking at the results. So, gamma 0 should still be roughly normally distributed, and we could make a little practice of looking at its value. it's no longer directly comparable because of the way the random effects are working. So if we tried to compare it directly, we would find that they're not quite directly comparable. But gamma 0, when I'm fitting these models, I'm looking around for evidence in all the marginal posteriors that my attempt to be diffuse on the priors, did it create some anomalies that I didn't want to be in there? So I look at this picture here and I say, oh, that looks like a pretty nice Gaussian, and that's what I would have expected if everything was behaving correctly, because the likelihood function is supposed to look sort of like a Gaussian with a lot of data, and so I'm happy with that. Okay, so that was gamma 0. Gamma 1 also looks like a normal curve, and it has an interesting value that suggests where things are headed now. What would be your intuition about the multiplicative effect parameter, the one we really care about in this model scientifically, compared with its interval? What interval are we going to get for it here compared with its interval in the fixed effects model? Would they be centered at about the same place? Yes. You'd hope so, because the random effects had mean 0. And so the center of the interval should be around the same under the fixed effects and random effects models. But which model would you expect to have wider uncertainty bands for the thing we really care about, the fixed effects model or the random effects model? Got to be the random effects model, because it's doing a better job of describing the actual heterogeneity present in the data. The Poisson fixed effects model pretends that the variance is equal to the mean, and that's an unfair pretend in this model. And so the uncertainty bands from the Poisson should widen to reflect the fact that actually we have unexplained heterogeneity in both the treatment and control groups. And that shows up here because, again, the multiplicative effect is driven directly by its e to the gamma 1, right? And so, look, the estimate, the signal is about minus 0.197, but the noise is now, oh, it's up to 0.11. And the signal-to-noise ratio is no longer bigger than 2, which is your standard knee-jerk place for it to be for usual sort of stat sig with things that are Gaussian at the 0.05 level. And look how the 95% interval for gamma 1 now runs from a negative number to a positive number. So things are no longer stat sig anymore. But you remember they were only sort of barely stat sig when we imposed the incorrect Poisson assumption, so no surprise. But I'll sort that all out in a few minutes. All right, what about, I'll wait for lambda to the end because it has so many components to it. Lambda.c should have exactly the same point estimate as before, but now its uncertainty band should be wider because we're working with the random effects framework. And in fact, if you compare that with the previous posterior standard deviation, you'll see it's wider now. We used to be getting numbers like 0.05. Now they're about 0.065. Lambda.e. And everything is nice and Gaussian, but again, it has uncertainty bands. Well, this one I think is a little bit wider, but the other one was noticeably wider. And notice also that with 100,000 draws on these things, we're again getting Monte Carlo standard errors on the order of 0.0005, so we're learning quite a lot about these parameters. If you wanted to report this, the 6 is very secure in the 0.6148, so is the 1. And the 4 is not quite secure because the standard error is of the form 0.0005, and that could bump the 4 either down to a 3 or up to a 5. So it's around, I would report 0.615 on that number with that size Monte Carlo standard error and be done with it. Okay. Now let's look at sigma.e. This is the payoff parameter about whether we need the random effects model. Oh, there it is. There's its posterior density. Here are its stats. If the fixed effects models were correct, sigma.e should have been around what? 0. Instead, our posterior estimate of it is 0.68 with a posterior standard deviation of only 0.07. Does it look as though there's any posterior mass at all anywhere near the region of 0? Certainly not. The random effects model fits the data overwhelmingly better than the fixed effects model does, and it shows up right there in that picture right there. Notice that this Monte Carlo standard error is quite a bit bigger than the other one. It used to be 0.0004 or something. Now it's 0.001. Here's why. Look at the autocorrelation function for sigma.e. It's our worst one yet. This is like an AR1 with a first order autocorrelation of about plus 0.95, maybe plus 0.97. Very bad mixing. And yet, with 100,000 draws, we're still getting Monte Carlo noise down to 0.001. So basically, you know quite a lot about what's going on here. I would certainly estimate the value to be 0.68, give or take about 0.073. I'm pretty happy with that, or maybe 0.07. So this answers the question about which model is better. And you can even make this formal if you want, but basically this is a kind of very powerful informal way to see that the random effects model is a lot better. Tau.e was just technical. It's going to have a sort of a nice looking long right-hand tail shape as well. Not very interesting to talk about it very much, so I won't say any more about it. By the way, no evidence whatsoever of any anomalies that came about by using that gamma epsilon epsilon prior. The posterior is so strongly, the likelihood so strongly concentrated away from zero that the gamma epsilon epsilon prior has done a really good job of being diffuse. I'm happy with it here. What about the lambdas? And then I'll finish with the multiplicative effect. That's the real payoff. Well, there's going to be a lot of them, and so when I click on the density picture, it takes a little while for it to figure them all out. But here they come, and I could get this out of the way, and we could actually look at them all. Just kind of scroll down through them. Because they're all quantities that have to live on the positive part of the real line, you'd expect them all to have long right-hand tail marginal posteriors, and they do. Everywhere you look, you just get the same sort of long right-hand tail shape. So the densities aren't actually that interesting to look at. They all look just like you'd expect them to. I don't see any anomalies. But what about the posterior means for these guys? That's going to be interesting. Before we get them, let me ask you what you think we should see. This is like saying everybody has their own lambda, except that all we know is that the reason they have their own lambda is that they had probably different covariate values on things we couldn't estimate, on things we couldn't actually measure. So what do you expect to happen with the lambdas? We're trying to fit a model in which everybody in the control group is allowed to have their own lambda. But all we know about these people in the control group is that they were in the control group and what their Y value was. So suppose I showed you two people who were both in the control group and both had a Y value of 0, for example. What would you expect for their lambda values? They have to be the same, right? The posterior for each of those lambdas has to be the same because there's no information whatsoever to discriminate between them. So basically what's going to happen is in the posterior for the lambdas, there's going to be a little cluster of them for the way the lambdas behave when the Y was 0, and a different cluster for when the Y was 1, and a different cluster when the Y was 2, and so on. And those clusters will all be a little different than the ones when X was equal to 1, the people in the experimental group. And if you spend some time staring at these numbers for a while, you'll discover that indeed that is what is going on. You get a whole bunch of, I think I put all the data in so that all the zeros were first, for example, in the control group, then all the zeros, then all the ones, and so on. So look at how all those guys have exactly this, the lambdas have practically exactly the same mean, and it goes on like that for a really long time with exactly the same posterior standard deviation as well. And then all of a sudden, look, it jumps. Now we finished all the zeros. There must have been 138 zeros in the control group. And remember, that was the number. There were 138 zeros. And so the moment we get from all the zeros to all the ones in the control group, now and notice that there's a shrinkage going on. The observed Y was 0 for all those people. And what's the observed lambda, the estimated lambda for them? It gets shrunken by all the way from 0 to 0.67 toward the overall mean for everybody in the control group. What about the people who had a 1, for example? Well, they actually get shrunken downward because the overall mean in the control group was a little bit lower than 1. And then we run through all the people who were 1s. Now these are all the people who were 2s. They got shrunk a lot. Their 2 got shrunk to 1.23, and so on. You can go through here and just exactly, it sharpens your intuitions about what these things should do. And the more you think about it, it does exactly what it should do. So pretty cool. And now finally the payoff. What's the posterior on mult.effect, which is the thing we care about, the thing we would publish? if we thought this was a good model for the data, and I will show you in subsequent weeks that it is actually a very good model for the data. Well, it has exactly the same point estimate as before. We estimate that the multiplicative effect of being in the treatment group is that it takes your control prevalence of having hospitalization and diminishes it by about 18%, but 18% give or take about 9%. And now the interval for this on the multiplicative scale runs from about 0.66, the two-way interval runs from 0.66 all the way to 1.02, barely including 1 again, and so we're back in the world in which we don't quite have stat sig if we look in both directions. But Dr. Peterson exhaustively examined the nature of the IHGA intervention, and when you read his paper, it was sufficient to convince me that it's quite unlikely that there's a downside to this. And so I actually find it more interesting to ask the question, what is the posterior probability that the multiplicative effect in the population is less than or equal to 1? And that's like computing the area under this curve right here to the left of 1.0, and that seems to be what, a big number or a small number or in between? Quite a big number. Comes out about 0.96, something like that. So, in fact, I would argue that the evidence is running strongly in favor of this result being generalizable in a valid way to the collection of everybody in Denmark with who is elderly and non-institutionalized, and this was the basis on which the Danish government decided to go forward. Indeed, I think in one of the earlier models, I don't want to save that change, and grab this guy here and kill it off. Oh, and this here and kill it off. We can sort of get out of this completely and go back to the course web page. There's some more stuff for you to look at here in which I show you what the screen dumps are for all this stuff. And we end up with the conclusion that when we compare the fixed effects and random effects models, the fixed effects model had just about exactly the same point estimate, but its uncertainty band was unnaturally narrow because of the incorrect Poisson assumption. The austere distribution turns out to have quite a lot of mass to the left of 1.0. So the last thing I did, and I don't think we have time to do it today, is I used a model in which I put a uniform prior on sigma.e from 0 to 2 instead of the gamma epsilon epsilon prior on the tau parameter. And I also put in one of these things that monitors what the posterior probability of having the value be less than 1 is. So I use the step function on the quantity 1 minus multiplicative effect, and I keep track of that and ask how often is the multiplicative effect less than 1.0. And the answer, when you run this code, you can do it for yourself, turns out to be about 95, 96, 97%, something like that. So pretty strong evidence that, in fact, the IHGA intervention is good not only causally in this particular set of people, but also we can project that and say it's probably causally the same sort of thing would happen on everybody in Denmark who were similar to the people in the study. So we're just about finished for the day. A reminder that after all of our wandering in the desert to Crane Beach and Blue Water and Araujo, we are done. We get to go home to Beacon Rock for the next 4 weeks in a row. So I'll see you guys next Friday at Beacon Rock. And throw the floor open for the last few minutes to questions or comments on what's happened today. What I just showed you is a class of models that would have been quite hard to fit even 15 years ago. And now they're utterly trivial to fit. You just take the fixed effects model and add plus EI in the WinBugs file and propagate the right assumptions about that straight through. And you get a very satisfying model for what's going on in the data by the device of bringing in random effects to mixture models to describe heterogeneity. Anybody question or comments? You look like you got something.
So you went through 4 different models for this particular on your site.
Gaussian and fixed effects, Poisson, additive and multiplicative, and now this guy, yep.
One of them you wouldn't have done for sure, but if you've done this in practice, Would you have gone through the other three? Would you go through 20 of them? Would you spend all your time thinking? What's your approach?
If I had been alert in the table showing that the variance to mean ratios in the sample were a lot bigger than 1, I wouldn't even have bothered to fit the Poisson model. So I would have gone directly to, since I'm comfortable with random effects models, I would have gone directly to the sort of random effects framework I have here, or else tried the separate negative binomial models like I showed you before. We could also do the negative binomial thing in here by putting gamma distributions on the lambdas instead of log, normal distributions on the log lambdas. We could go back and fit that model in WinBugs, and that would be actually quite a direct way to work with the data on the correct negative binomial parameterization. So that's what I would have thought of first. Now the issue of how to shop around, cheat essentially, and shop around in the data to look for a good model, end up iterating until you find a good model, and then pay the right price for having shopped around in the data is something that we're going to begin to address next time. So we've now gone 6 weeks out of the 10 with the cheating method, and it's time to stop cheating. From now on, we're going to talk about real-world methods for coping appropriately with uncertainty in the model specification process. Yes? Comment what? About overfitting. So he's asking for comments about overfitting. Overfitting arises when you fit a model that bends its will too closely to the data at hand and thereby does not generalize well to other data that might arise in the future from the same data generating process. I am not bothered about overfitting in this model here because it has so few parameters in it and the structure of the model comes out so naturally from the science of the problem. But to be sure that I haven't overfit, what I would like to do is some sort of Bayesian form of cross-validation, which is what I'm going to show you starting next time, in which I partition the data set into several different subsets, and I do modeling work on part of it, and then I look and see how well those models make predictions. How good are the predictions of those models on other parts of the data that were not used in the fitting process? And that's, in my opinion, that's one of the strongest ways to avoid overfitting. You will discover if you overfit, what will be the symptoms if you overfit, and you try to build predictive intervals for new data, what will they look like if you've badly overfit? They will tend to be far narrower than they should be on the new data because you have constructed intervals that are really nicely tailored for the data that you've got, and they haven't accepted the fact that the new data is actually going to be sufficiently different from that you aren't ready for it yet. So what will happen is that your alleged 95% intervals will actually only cover 50 or 60% of the time, and that'll be a really strong indicator of overfitting. Great. Thanks for coming. See you next week.